So far, we talked about the solution of this LQR control design problem, which was the controller that minimizes X transpose X plus U transpose RU dt X dot equal to AX plus BU. And we saw that the solution became, interestingly, in the form of state feedback, where the K matrix, if we assume the N matrix that you saw in the generalized form is equal to 0, this is equal to R inverse B transpose P, and P was the solution of algebraic Riccati equation. So to arrive at LQR, we could also look at this alternative problem that we have this system X dot equal to AX equal time AX plus BU. And then, this control goes and states comes out. But let's say we want to focus only on some of the states. And these are the states or a combination of the states that we want specifically to keep small. We want to keep small. So in this case, we could write our objective as design a controller that minimizes this Z transpose Z, which is the size of the portion of the states or a combination of the states, this vector Z that we want to keep small. And then now that we know how to also pay attention to the controller, we want to make sure while we are minimizing the size of the Z, we are not spending too much control. So for example, we could penalize the expenditure of the control using a term like this one. And this is for a system that evolves according to this thing. So if you look at it, the objective functions might look a little bit different. But if we do a simple substitution, we would arrive at pretty much the same objective function. So this is going to be so this serves as our Q matrix, and this is our R matrix. So here, once you have this formulation, then in this case, again, the control is going to be given exactly with this same solution that you have. Now, the Q matrix and R matrix are specifically given by this thing. So when we are talking about a system that we are focused on the minimizing the states, the states, or a subset of the states, there's always a question that what about the stability of the closed loop system? So what about if I put this K matrix? So if I just, similar to what we did with full state feedback, if I put this matrix in this feedback with the specific values that I have, and I end up with A minus B KX. And I'm going to put a star over here just to remind us that this is a gain that is designed by the LQR problem. And now the question is this matrix Horvitz? Is this system going to stay bounded and go to zero if I use the optimal control? Because in this process, we didn't explicitly see this being enforced. As it turns out, we have this theorem, which I am going to write it, and you can also find it in my notes, which says that if AB is stabilizable, and AC is observable, where here C is Q is equal to C transpose C. So we are focused on a specific C, the C that either we used in the states that we wanted, the subset of the states that we wanted to keep small, or if we take the Q matrix and decompose it into this format, we're going to call this decomposition, this basically multiplication between a transpose of a matrix and matrix itself. This is going to be our C matrix. So if this C matrix is observable, then the unique solution of the Riccati equation exists for algebraic Riccati equation, and the closed loop system A minus BK star matrix is strictly Horvitz, meaning that even though we didn't do eigenvalue design, this matrix is going to have all eigenvalues with negative real parts. So this is reassuring and also giving us a guidance that under what conditions we could have a stabilizing LQR control. When the problem is cast from the perspective of keeping some subset of the states or a combination, a controlled component of the system small, we could see the reason that why a C has to be observable, because ultimately when A minus BK star is Horvitz, it means that the entire state of the systems are staying bounded and going to zero. Now we are focused on minimizing a subset. So if AC is observable, it means that all the states are represented in this Z matrix. So by keeping the Z matrix bounded and small and forcing it to be closer to zero, technically, because it's a representation of all the states of the system through the observability condition that the system has, then we need and we are enforcing all the states to be bounded, which could only accomplished by when this gain that we have will make this closed loop system Horvitz. So with LQR design, then we are accomplishing two things. We are stabilizing the system, and also we are enabling us as to have a mechanism that we also regulate the size of the control that we want to spend in achieving our objective.